In this problem, we have a disk of radius 0.5 meters that rolls without slip on a horizontal floor with a constant clockwise angular velocity of 3 radians per second. There's a rod attached to the disk at point A, and the end of the rod at point B slides along the floor. Determine the angular velocity of the rod when OA, the center of the disk, and point A is horizontal. All right, so we have this figure that kind of explains what's going on. We have a disk, it's rolling, it's pulling this rod behind us, and we want to determine what the angular velocity of that rod is. And we know the angular velocity of the disk, the radius of the disk, and the distance between O and A. All right, so what we want to do is get familiar with the system by drawing a figure that includes the IC, the velocity directions, and a coordinate system. All right, so this disk rolls without slip, so there is an IC between the ground and the disk. So therefore, if we draw a line between the IC and any point, we can determine the direction of the velocity. So that'll be perpendicular to that line, so perpendicular. All right, this IC is not an IC that's attached to the rod, so we can't use it to find directions of any of the velocities there. But what we need to do is apply the relative velocity equation between points that we know and points that we don't know. So we know what's going on at the IC. So we can go from the IC to A. And then we can go from A to B. And at B, we can apply a geometric constraint that says there is no vertical component of the velocity. The velocity is all in the X. All right, so the disk rolls without slip. That means the velocity of the center of the disk is V equals R omega. We can apply that to find out what the velocity of the center of the disk is. So now we can either go from the IC to A or from O to A. O to A is kind of simple because our position vector is just in one direction. So we might decide to do that. All right, so we're going to go from O to A, but like I said, we could also do IC to A. Either one would work. So apply the velocity equation, VA equals VO plus omega cross RA relative to O. And RA relative to O is just in the minus X, and minus K cross minus I is J. All right, so we get the velocity of A. Now we know A, so we can go from A to B. So we use the relative velocity equation to go from A to B. The rod angular velocity I have assumed to be clockwise, so that would be negative K. And to get from A to B, we're going to go minus 2 in the I and minus 0.5 in the J. So that's how we get from A to B. Oh, and this should be RB relative to A, not RA relative to O. So RB relative to A. All right, and we apply the cross product and get an equation that has omega r as a variable. All right, now we have a geometric constraint at B that says there is no vertical component or y component of the velocity. So we can apply that. So the j component is 0. Pick out all the j components from the velocity equation, and we can solve for omega r. We get a negative. So that means the direction we assumed is incorrect. So instead of omega r going in the negative k, it will go in the k.